Yeah, so in the previous lecture, we defined the Poisson bracket, and then we reformulated if we may in terms of the Poisson bracket of P and Q with respect to the Hamiltonian, which is an observable, telling you how position and momentum evolve in the phase space as a function of time. Any questions about this? The goal of this reformulation was to see that basically the leap to quantum mechanics would look natural, would correspond to promoting or going from sending the Poisson bracket, replacing the Poisson bracket with 1 over IH bar commutator, right? All right, so here's a table that compares classical and quantum physics. States of classical, so the configuration space in classical physics is a phase space, in quantum mechanics is a Hilbert space. States are in classical physics are probability distributions on the phase space that we wrote with W because we have too many P's in this discussion. Analogously in quantum mechanics, it's a density operator. Probabilities are functions that are everywhere positive and integrate to 1, right? And density matrices are positive operators and they trace to 1. Right? So trace is the analog of integration or summation. Observables are functions in the phase space, more precisely smooth functions in the phase space, actually measurable functions, but it doesn't matter. And we set real functions. Oops, sorry. So these are real functions. And analogously, observables in the quantum realm are Hermitian operators, and the reality conditions becomes Hermitian because Hermitian operators, as we proved, have real eigenvalues. There are expectation values, which are basically found by integrating the observable next to the probability density, probability measure, right? That's just the expectation value in the phase space. Analogously, we said trace plays the role of the integration. So when it's natural to expect that the expectation value is trace of A rho as we derived. By the way, an observable can always be written. What's the information content of an observable? An observable is a Hermitian operator. How do you describe to someone a Hermitian operator? What's the information I have to give you to tell you what the Hermitian operator is? Yeah. Spectrum, eigenvalues, what else? Eigenvectors, exactly. If I tell you that all the eigenvalues and all the eigenvectors, I've given you the observable. Eigenvalues are precisely the classical things that we see. These are the real functions we talk about, right? So what quantum mechanics brings to the table that goes beyond quantum mechanics is eigenvectors, right? That's a brand new concept. That's quantum mechanical. Eigenvalues are the analogs of these real valued, real functions. Good. So we also, the point of this comparison was that we wanted to talk about dynamics because this is a new chapter of the book or the course. And we said that we could do this in 2 different ways in classical physics, even classically. We could assume our state, which is our probability density, is static, time independent, and our observables, our functions evolve as a function of time. In which case, the equation that we have is this: dA dt is AP. This is the case where the Hamilton equations of motion that we derived, right? We wrote down evolution for P and Q. Those are observables, distinguished observables. We actually wrote it for an arbitrary observable, right? What was dF dt? Classical physics. dF dt is Poisson bracket of F and H. And because F could explicitly depend on T, you have to add a partial derivative just in case it depends explicitly on T. Good? All right. This is what we call the Heisenberg picture. Equivalently, you could describe it different using a different language, which is a setup where states evolve So now it's a probability distribution that evolves as a function of time, but the observables are time independent. We call this Schrodinger picture. And the evolution equation we wrote down for that was minus. Oh, sorry. All right. Quantum mechanically, the equations are somewhat similar. This is the Heisenberg picture equation. All we've done is that we've replaced the functions with observables, and we've replaced the Poisson bracket with 1/1 IH bar commutator, right? So I haven't explained why. At this point, it's an observation, but we're going to derive this, okay? But this is just to, in anticipation for that derivation, I'm telling you how to connect it with what you already know. Similarly, you could write down the evolution equation for the density matrix. Is what you would expect from this formula if you send the commutator to 1/IH bar, right? There's an extra minus sign. The minus sign brings the I from the denominator to the numerator. For pure state rho, the density matrix is ket alpha bra alpha for pure state alpha. So if you just write down this evolution equation, Heisenberg equation, you find that this is satisfied if your ket satisfies the Schrodinger equation. We're going to derive this today, just from basic principles of quantum mechanics. Okay? So this is the summary of the previous lecture. Are there any questions? Yes.
What's the difference between dynamics?
So physicists throw that term quite a lot. Let me give you a loose, I can tell you what a physicist means when they say dynamics versus kinematics. Kinematics is something that is fixed by the symmetries. If some behavior of the system as a function of time is fixed by the symmetries, implied by the symmetries, we call that kinematics. If it's not fixed by symmetries, then we call that dynamics. But there's no sharp term here, right? From the point of, for this course, every time we say time dependence, we're talking dynamics, all right? So the term kinematics doesn't exist for this course. That's like a research term that people throw somewhat actually arbitrarily. It's more slang in the community. All right. Any other questions? Good. All right. So this was just motivational because when I was learning quantum mechanics, I wish I had some motivation. So now we're going to derive this, right? And even though I'll try to follow, I decided to follow a path that's closer to Sakurai so that it can ground, because we went off Sakurai for one lecture. This way you will be more grounded. But I want to insist that I could have literally done this analysis identical to derivation, to the translation operator in quantum mechanics and how we derive momentum operator, right? So the way we derived the momentum operator in quantum mechanics was that we considered translation operator. We did a bunch of like manipulations, and then we found there is an uncertainty relation, there is a momentum operator that generates translations, blah, blah, blah. And we saw 1/H bar. This analysis is basically identical to that, but for some reason, Sakurai uses a different set of words, so I'll use Sakurai's words because just to help you guys have a reference to follow closely. All right. So first, I can't emphasize this enough. Time is not an operator in quantum mechanics, as opposed to X position. Time is not an operator. We do not promote time to an operator. Position we do, right? This, okay, good. We will see that the conjugate variable to time becomes, what is the conjugate variable to time? Hamiltonian energy. That becomes an operator, but not time, right? This will pose a problem and give us hell the moment you try to do relativistic quantum mechanics, QFT. That's another story for another day. Over there, we have to make X again a parameter so that we could treat time. Time is never an operator in any formulation of physics. Time is always a parameter, okay? All right, so we're gonna be working in the Schrodinger picture, meaning that I'm gonna be talking about the evolution, time evolution, and time dependence of kets, right? That's what I'm gonna be talking about. Good. So imagine some ket alpha at time t naught. This is my notation for representing a ket, a pure state at named alpha at time t naught. For example, okay, yeah, I don't need that example. At some later time, t for t larger than t naught, it goes to alpha of t, but to just keep track of everything, I just put alpha of t naught is what I started, then I evolved it to time. Of course, this is all consistent if you take the limit of t naught going to t naught, you recover your state, right? So now, good. It's just notation so far, just to get the notation. Similar to what we did before, we talked about last time when we were talking about position, we had the x hat, x primes, and then we defined a translation operator that shifted this value. Now, we don't have a t operator, but we could still use time as a parameter to label our kets, as I just did. And you could define a time translation operator. I'm going to write it this way. This time translation operator has two labels, t naught and t. It means that it acts on kets at time t naught and moves them, evolves them until time t. Good? So here's a notation. Let's make sure everybody follows this. Is this clear? So all I've done, I can define this operator the same way that I could define translation operator, right? It's not an observable. We'll see in a second. Translation operator was not an observable either. Why? Why is translation operator not an observable? What's an observable? It has to be Hermitian. Good, somebody answered. Thank you. It's not Hermitian. What was the translation operator? It was e to the power of I p alpha. What is the dagger of this? It puts a minus sign up here. It's not equal to itself, so it's not Hermitian. It's not observable. Okay, good. So we similarly define a time translation operator, and we'll see that this will not be an observable either. However, the same way this was intimately related to an observable, P, here it will be also related to an observable in the exponent. That's going to become a Hamiltonian. So what are the properties of this? First thing is that if the initial ket was normalized meaning that its inner product with itself, its length, its norm was 1, it should remain norm 1. Why is that? Conservation of probability, right? The normalization of the vector is just the probability is adding up to 1. Is that clear, or do I need to explain? Okay, good. But of course, every coefficient, like take this ket and expand in some eigenbasis. So every coefficient evolves in time. However, this condition, which is the normalization of the ket, right, has to remain fixed. The total sum should remain fixed. That's the conservation of probabilities, right? So in other words, alpha t naught t bracket with itself should be the same as alpha t naught, right? I can bring out the u and u dagger from these guys, and I end up with this equation. This equation is always satisfied if u dagger u is 1, right? So this already tells you that your time translation operator is unitary. because U dagger U, and similarly you could argue that U dagger has to be 1. How do you argue that U dagger should be 1? Reverse time. Yeah, you just have to reverse time. Okay. Good. Everybody's with me? Over there, when we were doing the translation in space operator, that was also unitary by the same analysis argument. It should also have to satisfy the composition property. It means that time translation from time t0 to t1, followed by time translation from t1 to t2, should be time translation from t0 to t2, right? That's just a composition property. Good. So basically, these properties already tell you there's a group. The group is R, if you know group theory, but good. Everybody's good. And also, another thing that I do know is that the limit, I wrote this, right, of t going to t naught, of u of t naught should be, someone? Identity, exactly. Thank you. Good. So now that I know that, exactly similar to what I did before, I'm going to expand it around the identity. That means time evolution for a tiny amount of time, an infinitesimal time evolution operator. Good? So what I'm going to do is I'm going to take the infinitesimal time translation operator. I played the same trick before. Write it as identity minus I some operator dt. This operator has to be Hermitian. This omega hat has to be Hermitian. Previously, when we did that to translation in space operator, we gave it a name. We call it the K hat, right? And K hat was related to momentum operator by H bar. We'll see that the same will happen here. It becomes related to the Hamiltonian up to an H bar. Why is this Hermitian? Yeah, there are various ways of saying it. You say what you say is correct. Another way of saying is that if you do U dagger U, it should become identity to the first order and dt. That will force this to be self-adjoint. Is that clear? Right? Let me do that on the board. Take U dagger of T naught plus dt T naught multiplied by U of T naught plus dt T naught. Right? So what is this? This is identity plus, well, plus or minus, so define minus. Minus I omega hat dt dagger identity minus I omega hat dt. When I take the dagger, the sign flips, and also I get the dagger of this guy, right? When I expand this, I obtain identity plus I omega dagger minus omega dt plus order dt squared. So if I want U dagger U to be identity to the first order, U omega has to be equal to omega dagger. It should be Hermitian, right? Oh, that was a comment that was made earlier. Okay. Very good. Now, what is the dimensionality of this operator omega hat? It's frequency. Why is it frequency? Yeah. Exactly. Okay. Well, yes. if I'm adding identity to omega hat dt, identity which has dimension 1, dimension I'm just note it's dimensionless. Sorry, it's dimensionless. Should have the dimension of omega times time. What is so omega is inverse time, aka frequency, right? Now, what is the thing that we do know? So previously, if you recall, what we had was that we found that the dimensionality of that K operator, the generator of translations, looked like momentum up to an H bar. Here, we have this relation, the so-called Planck-Einstein relation. I wouldn't give it that name, but anyways, Planck relations is the H bar omega. So it looks like E over H bar or Hamiltonian over H bar is a candidate for that omega hat. Indeed, that's the case. Now, at this point, right? So what we find is that the time translation operator, infinitesimal time translation operator, is identity minus IH hat dt over H bar. Hamiltonian generates time evolution the same way that momentum generates translations in space. Time translations, yeah. Good. At this point, you could complain. You could complain that a priori, this H bar need not be the other H bar, right? H bar was just some dimensionful constant, some constant that was in quantum mechanics that had the right dimension. It turns out that it has to be the same H bar, otherwise this simple F equal ma rule will not hold. What is this equation? On the left-hand side, it's about time evolution. On the right-hand side, momentum appears. Right? Here, the H bar of the previous discussion comes up. Here, the H bar here comes up. So they have to be the same. There's only one constant in quantum mechanics, and that's H bar. What is the value of it, by the way, in metric units? Anyone? It's tiny, right? I'm going to double check to see if I'm not making things up. Anyone? No? Yeah, 6.6 times 6.6 or something like that times 10 to minus 34 in SI units. So it's teeny tiny in SI units. SI are natural for people of our size, right? Good. So it's teeny tiny. Quantum effects are small. Very good. Okay, very good. The left-hand side has the X hat operator evolve as a function of time, right? That means that's related to infinitesimal time translation operator, right? And this generator that we just discussed comes up there. And there will be Hamiltonian. And the corresponding H bar of the Hamiltonian. The right-hand side is momentum. Momentum is the generator of spatial translations, right? And the H bar of that one appears. So if you have any desire to make this equation work, you would have to set the two constants to be the same. Yeah. Should be permission. Okay, so U dagger U for infinitesimal dt has to be identity. Why? Because it's a unitary operator. So I just expand this. I define omega hat this way. This was just a very definition of omega hat, right? Here I have to put the same thing dagger. When I put the dagger, the sign flips, and this one takes a dagger. All right, so here. I have to expand this. There are four terms, right? Identity is identity. There is the I omega hat dt term, these two, and then there are this term that's here. The last term is order dt squared that we won't care about, right? So this thing has to be equal to identity. which forces this to be Hermitian. Any other question? Yeah.
Why do we throw out the OGT squared root?
Because it's infinitesimal. This is just the standard. So yeah, this is the standard way of dealing with infinitesimal calculus. This is derivatives calculus. Good. I'll try to squeeze a homework problem about that. I thought I did. Maybe I have. The Trotter formula. What is the Trotter formula? As physicists, I think you guys should learn this stuff. Oh, well, actually, I want to get to the end of the lecture. All right. Any other questions? So far what we did was we defined time translation operator, and we showed it's related to the Hamiltonian when we do infinitesimal translation up to this factor of h bar, dimension full parameter, the constant that controls quantum mechanics. By the way, the fact that h bar, so what is the formula? The formula is h t over h bar, right? This means what? H bar is tiny. It means that the time scales that we measure a second is an insanely long amount of time for quantum mechanics. A lot happens quantum mechanically. So quantum mechanics is fast rather than slow, right? Quantum phenomena are controlled by T over H bar. Things happen really, really fast. In a sense, too fast for you to see them. That's what classical world emerges. But you try to build intuition. I mean, this is at the level of this course that you just learn about the Hamiltonian operator. This is the argument. But as you go further, you learn that it's an unsolved problem. Yeah. Anyone? Oh, yeah.
This process of doing a decimal change or evolution, is that how you find these conjugate pairs?
Yeah, absolutely, absolutely. Right. When I was doing that, I said this is fully general, like completely general. Previously, for me, last time I started with an observable, right? Then I took the corresponding eigenkets x prime, right? The observable was x hat, and then I defined translation operator. This time around, there was no time observable, but I realized that I can still label my kets with the parameter t. So I can define an operator that shifts that parameter, whatever the hell it may be. Turns out it's Hamiltonian. Good? All right. So now that we derived this, we're just one slide away from Schrodinger equation. So what do we need to do? We take the time evolution operator from time t to t naught, and the time to evolution operator from t naught to t plus delta t, and subtract them. This tells you how different is time evolution from yesterday until now compared to yesterday until now plus epsilon, right? If you just plug in what I've given you, you learn that this thing is just minus I h bar dtu. Is that clear? Why? Actually, it's one liner. You see it? Should I derive this? All I'm doing is I'm using a composition rule. So this is the composition rule, tells me that this is t plus dt, t u of t naught minus u of t naught, right? This one was identity minus I h over h bar dt. I'm going to factor this. becomes minus identity u of t naught, identity and identity cancel. Right? All right. So from this, you learn that the time derivative of the time evolution operator times IH bar is Hamiltonian times U. Right? Good. So now let's act with this on a kit, alpha of T naught. Left-hand side and right-hand side, if you act with it, you just learn that here's your equation, which says that the time evolution of a ket at time t times IH bar is H Hamiltonian acting on it. H is an operator, right? Hopefully it's clear. If I just take the bracket of this with x prime on the left, I find the good old Schrodinger equation, right? That you probably recall it from in this way. So the wave function of the ket alpha in your favorite basis, I don't care which basis, we usually write that Schrodinger wrote it in position basis, right? But by now you know that you formulate the equation for the ket. So your favorite basis minus IH bar is H acting on that. Good. So I can't insist this enough. So what is quantum mechanical about this equation? There are two things that are profoundly quantum mechanical. One is H bar, which points to some really, really fast physics, right? Very, very small time scales. The other one that's deeply quantum mechanical about this, I've said it a million times already, is I. Right? So I just want to make a comparison. We don't have time to spend too much time on this, but what is the free particle Hamiltonian? G squared over 2m, right? This is the equation I'm dealing with for a free particle. Have you seen an equation that looks like this in physics before? If I replace this with a minus sign, right? All the quantum physics of it with a minus sign, it looks like diffusion. There is a nice connection between diffusion equation and Schrodinger equation. The difference is that diffusion acts on probability densities and they relax. I could have included this as an item in my comparison of classical and quantum physics. Here, the fact that this is I, it means that phases evolve really fast. So in quantum mechanics, the fast physics has to do with phases. When you put a kit, prepare a kit at time t0, instantly try the phase of it goes nuts. All the phase coefficients in the energy eigenbasis, you just go really fast, right? That is a quantum effect. Good. Any questions? I have to pause here for questions. Diffusion question? Yeah. Diffusion. DIFUS. Right? Yeah. 2x. Wait, what? Oh, yeah, diffusion. Okay, diffusion. 2x. Yeah, 2x, 1s. All right. Good. Any questions? So the remainder of this lecture is going to be about solving the Schrodinger equation First, I'll build up a limit, right? I'll build up a limit. I'll solve it in three different levels, and I work out an example, right? So first setup. So what is the equation we're trying to solve? Schrodinger equation. It's this. This is the equation we're trying to solve. Is this clear? So the kets are time dependent. I'm just suppressing them. First case is when H has no explicit time dependence. Hamiltonian is time independent. For instance, p squared over 2m, a free particle, right? Give me an example of a free particle that's subject to a force that's time dependent. Put it in potential that's time dependent. Put it in some background. Let's say you have a spin particle, and put it in some magnetic field that's time dependent, right? So if it's time independent, you could integrate this equation. How? Well, let me not write it on the board. The integration is basically this: exponential of minus IH over H bar T minus T naught. There are two ways to see this. First, you could just take this, put it inside the equation, Schrodinger equation, right? And see it's the solution. But another way of doing it is by observing that what is the time evolution operator? We said that for an infinitesimal time is 1 minus IH bar, IH Hamiltonian over H bar, dt. If I want the evolution from T to T naught, let me first break it down to a gazillion pieces. So that T minus T naught over this capital gazillion, this large number n, is tiny, infinitesimal. I can treat it as infinitesimal. Now, when I do that, my operator becomes minus dt, right? Remember that this is just T minus T naught over n. This multiplied by itself again, multiplied by itself again, so on and so forth. How many times? N times, because dt is T minus T naught over n. If you multiply n times, you go from T naught to T. So what do you need to calculate? You need to take the 1 minus IH over H bar T minus T naught over n to a power of n and take the limit of n going to infinity. This is that Schroeder formula I was talking about. Do I want to say it that way? No, it's not Schroeder formula. This is an identity. This is the very definition of an exponential. We had a homework problem about this, I think, right? I think I did. We did. Of course, those of you guys who solved the homework problem saw that. All right, so this is the time evolution operator. Now, is it unitary or not? It's manifestly unitary, right? What is the dagger of exponential of e to the power of IHT? It's exponential of minus I h dagger t. But h as a Hamiltonian is self-adjoint. Is that clear? Are these familiar words at least? So it becomes e to minus IHT. If you multiply e to the power of IHT and e to minus IHT, what is the answer? Identity. All right. Okay, so this is a time evolution operator for the time independent Hamiltonians. This is case one, the simplest case possible. What is it? What's the physics of time independent Hamiltonians? What is it? Well, as a physicist, what system would you write the time independent Hamiltonian for? Systems that's isolated from environment, right? A system that's just not talking to any environment. If it's isolated, it's just evolving by its own Hamiltonian. Good? So case 2, Hamiltonian depends on time. However, Hamiltonians at different times are compatible observables. The fact that I know the energy now of the system now does not limit my ability to know about the precise value of the energy tomorrow. Hamiltonian at different times commute. Time dependent. However, it commutes at different times. It's perfectly reasonable to ask to measure with arbitrary precision energy at all times. That's what it means that Hamiltonian at different times commute. For any T1 and T2 that they commute. Is that physics of it clear? Set up the context. The simplest example, motivation for this is that your Hamiltonian is often some coefficient, right, times some fixed H naught, right? That coefficient we often call a coupling in physics, right? That's a coupling. You could make that time dependent. Now, what for context for a setup like this, why is it that H at different times commute? Can you see why? Yeah, just couplings factor and H naught and itself commute, right? So what does G control? G controls the strength of the interactions, right? This we call it coupling. And then if you make it time dependent, then it's indeed the case that your Hamiltonian is time dependent. However, at all times they commute. How do you exponentiate? How do you integrate this equation? You basically simply exponentiate, but instead of minus I over H bar Hamiltonian T minus T naught, you should integrate the Hamiltonian. Is that good? How many of you guys know Baker-Hausdorff-Campbell? We'll have to put a homework problem. Students in QFT didn't know it either. That which blew my mind. But it's a method to expand exponential of an operator. Is this? Do you understand the physics of this mathematics of this exponentiation, or do I need to explain it? If it's unclear, just take it as a solution, plug it into the equation, and check that it's a solution. But if you don't see it, I think we won't have time to go over it because it's just some fact about differential equations and BC figure also Campbell. But I wanna stress, it makes sense to write down. Okay, let me give you a hint for those of you guys who want to think about this. When A and B commute, this equation holds. Good. If A, so here I'm integrating a bunch of Hamiltonians, right? So A Hamiltonian different times commute, I could just literally think of them as multiplying separately, right? Because what is this? Yeah, let me that. This becomes a time evolution operator for a short amount of time. This is a time evolution operator for a little bit after, right? If A and B, so this is a case where A and B do not commute, and this is A and B commute. If A and B do not commute, this is no longer true. It's no longer true. Actually, the equation that tells you what the right-hand side is called Baker-Hausdorff-Campbell, BCH, right? What you intend to do is the right-hand side because you want to multiply, you want the composition property. You want your unitary evolution to have the composition property. What you want is the right-hand side. Here, when they commute, you could repackage them this way. You can write down that elegant equation. Good. Now, when the most general case, sorry, is when they do not commute at different times, then what you would like to do is the right-hand side, which is, there's a trick to do it. Okay, so Freeman Dyson, he derived the right-hand side. He wrote down an elegant way of multiplying these guys, and he found this equation. This is the time evolution operator. We're not going to derive it now. We're going to derive it at the end of the semester. This is basically what it looks like, right? It's an infinite sum of integrals. Now, I want to point out a couple of things. As you can tell, this equation is ugly. As physicists, we don't deal with ugly equations. We figure out the smart way of repackaging it. And I want to tell you how to repackage this in your head, at least. Let's zoom here. What does it look like? Here are the insertion of operators. Hamiltonians at different times. There is the first integral, which is from t naught to tn minus 1. Well, okay, let me start from here. The first integral, let's say, is this one. It's t0 to t, and you integrate over t1. Oh, sorry, no, I have to do it from here. So you integrate over tn from t0 to tn minus 1. The next variable that you integrate over is dtn minus 1. Does this look familiar? If I have an integral that looks like this, what am I doing? What am I integrating? Something, f of x1. I'm integrating over a triangle. That's what I'm doing, right? A triangle could be viewed as one variable. In this case, y is always larger than x. Here, what is going on is that we wrote down that set of operators, h, t1, t2, blah, blah, blah. But it must be that t1 is always later than t2, always later than t3, and so on and so forth. Those integration rules impose that. Because if they don't commute, if I write a whole bunch of operators like this that don't commute, that sounds nuts. I have to have a tell you what the order is, right? Because they don't commute. The order matters. And the equation tells you what the order is. T1 is the latest. T2 is a little bit earlier. T3 is a little bit earlier. As physicists, we know about this equation. We don't need to memorize the form of it. We define this thing called time ordering operator. So what is this? It says, write the exponential, expand it. But every time you expand it, you have to time order things. Meaning what? Meaning that if I have two operators, O1 and O2, sorry, O at the T1, T2, if T1 is larger than T2, this is O of T1, T2. If T1 is less than T2, you reverse the order. It's a time-ordered exponential. Derive this without using time ordering. Turned out that before him, he passed away. He would not have liked this comment. Turned out before he did this, Feynman figured out the time ordering trick, and he just brute force. I mean, Freeman Dyson just brute force solved this equation. But Feynman knew about all of this, and he already knew how to write it intelligently. But anyway, he did not like that. Passed away a couple of years ago, actually. Unfortunately, I was there when he passed away. He was carrying a tray of food and he tripped. He was 96 though. Like it was, yeah. Towards the end, Freeman Dyson, okay. This is recorded. I should not say these things. He towards the end of his life, he said weird things. Very, very weird things. Like, yeah, I said crazy stuff. All right. Freeman Dyson. Okay, good. Any questions? Yeah, he one memory I can tell about him is that he was 96. He was still coming to the office every single day, and in the middle of a hot summer day, he would be bundled up with a hat and scarf. That's kind of like fun. Had a very British accent. All right. Any questions? If you want to know one of his fun, weird, bizarre ideas, look up Dyson sphere. It's kind of wacky. Yeah, I mean, probably some people in popular science have heard of Dyson sphere, which is kind of wacky. But anyway, all right. I did not say that. I might not post this video. All right. So good questions. I encourage you guys to think about time ordering. It's equivalent, right? And I explained what the physics of that those integrations are, right? Like these are integrations over like some triangle hyperdimensional version thereof. But the physics of it is just imposes some ordering. Those like when we teach QFT, we go over this in detail, but in practice, we force students to go through it in the homework. But, all right, good. So now what we want to do is we want to talk about, we said time is not an operator, but Hamiltonian is. It's not an observable. Hamiltonian is. So let's talk about energy eigenkets. Eigenkets of Hamiltonian. For some bizarre reason that's unclear to me, Sakurai loves to talk about an operator that commutes with the Hamiltonian and picking the eigenkets of that observable. You don't have to do that, but he does that. It's equivalent. Hopefully you know that it's equivalent, right? If I have an observable that commutes with the Hamiltonian, their eigenket, they're simultaneously diagonalizable, right? I can use their eigenkets for each other. Good? Is that good? We proved that. So everything will go through if you assume that Hamiltonian, you put E prime, you replace in Sakurai notation, replace A prime with E prime. These are energy eigenvalues, right? And just assume that you have no degeneracies, because degeneracies make this notation really awkward, right? But I just follow Sakurai's notation so that you could follow the text as well. All right. So here's your Schrodinger equation in this case. These are the energy eigenkets, and here are the eigenvalues of them. Now, if you want to know what the time evolution operator in the time independent case is, e to the power of minus iht or h bar, one thing you could do is you could put the resolution of identity to the left and right of it. In the energy eigenbasis, what you learn is that it becomes, this is one liner, you could follow that. It becomes sum over energy eigenkets of a bunch of phases. Now it becomes a little bit more clear when I said the unitary evolution operator is just a bunch of phases in the energy eigenbasis, but these phases evolve really, really, really fast. What is E times T? What is the dimensionality of E times T? Angular momentum or action. H bar has the same dimensionality. When E times T is, when we say H bar is small, we mean compared to E times T's in our world, right? Only a dimensionless parameter could be small or large, right? So E T over H bar is gigantic. These phases are just oscillating like crazy. That's responsible for the fact that this mug behaves classically. If the time evolution, if you observe this mug at very, very short time scales to make that ET small comparable to H bar, it would not act classic. It would show interference patterns and all sorts of wacky stuff. You will see in a second that this story I told you is a little bit more nuanced. Of course, you should expect that always. Any questions? All right. So now we take an arbitrary eigenket, an arbitrary ket, and expand it in the energy eigenbasis. This is the form of it. When you evolve it, there are a bunch of phases that are multiplying the coefficients of the expansion. you immediately learn that the energy eigenkets evolve by just a phase, right? Only a phase multiplies an energy eigenkette. Is that clear? What is the equation I'm solving? Schrodinger equation. The answer to that was obvious, but so IH bar ddt E prime. This is an energy eigenkette. I'm calling it A prime here for some reason because Sakurai calls it. This is my equation, right? Everybody's with me here. The right hand side normally would be H hat, but H hat is an energy eigenkette. Therefore, it's E prime. So what's the solution to this equation? It's just E prime is E to the power of minus E prime T over H bar. Run out of time. Right? So energy eigenkets evolve by phase. What does that mean for their expectation value of observables? If I have an observable and I measure the expectation value of it in some energy eigenket, what do I find? Constant time. It's time independent. Even though the ket evolves by an arbitrary phase, not arbitrary, time dependent phase, but the expectation values are independent of time. How do you see that? Here's the equation. Actually, yeah, I think I wrote it here. Maybe I did not. Let me write it on the board. I think I did write it somewhere. So take some observable B. Right? This will be E prime 0, E to the power of minus I E prime T over H bar. This guy will give you the same coefficient, same phase with a plus sign here. And the phases cancel each other, so this is independent of time. This is E prime of 0. This is such a bad chalk. I should bring some good chalk from out. That's horrible. So that's a sense in which energy eigenkets are stationary. Observables in this space, in these states don't evolve. If you're an exact energy eigenket. But the ket evolves with a phase. That depends on the energy of the eigenket. Unless the energy is 0, in which case, what is the phase? What's the phase of 0? 1. There is no phase. What is that state called? Ground state, vacuum. So what is unique about vacuum is that it does not evolve with time, not even with a phase. Yeah. Very good. Yeah. Yes. We learned something here. Another distinction between quantum mechanics and classical physics. In quantum mechanics, let me think about this for a second. Yeah, in classical physics, if you shift your, actually, let me not say this because they usually confuse you. No. All right, so I said what this. A general ket will look something like this, expanding the energy eigenbasis. So if you calculate the expectation value of some operator B, observable B, in the energy eigenket, how would you do this calculation? So on the left and right, you would have this E to the power of minus IHT, E to the power of IHT over H bar. You insert a resolution of identity where? Here and here. What you find are matrix elements of the observable B in energy eigenbasis the initial coefficients, and a bunch of phases that depend on the energy differences. Let's pause here because this is a very, very important equation. Right? What am I computing? I'm calculating the expectation value of an observable as a function of time in an arbitrary ket. That's what I'm calculating. As a function of time, right? So I take my arbitrary ket at time t naught and I expand it in energy eigenbasis. Right? So I know that the time evolution at some later time, it would be alpha of t naught multiplied by e to minus iht over t h bar. Actually, what is the time that I'm looking at this expectation value? One of the questions I've written down. What is the name of this ket? What's the ket in my notation? Yes. This is just alpha of t naught equal to 0. Similarly, here is the broad, right? That's what I'm calculating. I'm calculating the expectation value of the observable B in some arbitrary state at some time t. I insert the resolution of identity. Of course, it will depend on the initial state. These are the coefficients of the initial state. These are the matrix elements in the energy eigenbasis. There are these phases. So there is a very, very important lesson here. Let's see if as phases could extract it. I told you that the phases that you see are e to the power of I e prime times t over h bar. So I said e prime times t is very, very large compared to h bar, right? That statement was that was a zero, that was a naive statement. The more fancier statement is what appears, you don't observe a ket, you observe expectation. In the expectation values, you sum over expressions of this type. What you should call small or large compared to h bar is energy differences times time. This has dramatic consequences for physics. Drastic consequences. It's just insane. I cannot stress this enough. We'll come back to this when we discuss composite systems in quantum mechanics. The reason is that sometimes your energies are large, however, your energy differences could be very, very small. Good? This energy difference of course, gives you a frequency, right? E prime, the energy difference divided by h bar is a frequency that you associate with energy differences. So these frequencies control the oscillatory behavior of your observables, right? Any questions? In the remainder of, the remaining 7-8 minutes, I will just work out one example. This is a very important calculation. Right? I said, it's a very simple thing, but as usual, in quantum mechanics, it takes some getting used to, but a lot of it is working out examples and also staring at what you're doing. Interpreting, I absolutely recommend interpreting every single term you write down. Like, what is the physics of the CA prime star CA double prime? It points out the dependence of expectation value observables to initial conditions. CAs were your initial state, right? So you should, when you write down these expressions, if you want to understand quantum mechanics, try to interpret every single term in it. It's important. Well, okay, I'm not going to over-explain. Any questions? All right. Example. So what is the example we're going to solve? We're going to solve an example where there is a Hamiltonian. However, the Hamiltonian is time independent. So case one, the simplest case possible. Consider spin half particle, say the silver atom, in a background magnetic field, the same way that we actually tried to do the Schrodinger experiment. What is the Hamiltonian? The silver atom has an electron. So E is the charge of the electron, C is the speed of light, and E is the mass of the electron, right? S hat is an operator. It's a vector valued, operator valued vector, sorry. It's an operator valued vector. Dot B, B is just a vector, right? What do we have? We have a quantum system with spin. We put it in some background magnetic field. I'll be so impressed if somebody told me what the name of this kind of Hamiltonian is. Where you're dotting, you're putting. Well, maybe we'll comment on that later in the course. This is called semi-classical approximation. But anyway, the Hamiltonian is just a magnetic field, right? Coupled to your observable. Is the Hamiltonian clear? It's the same thing that we had for Schrodinger. I just went over it. I didn't discuss it. I just wrote it on the board and moved on. So now I'm going to assume that my magnetic field is in the z direction. That dot tells you that all I'm dealing with is S hat of z times b. B is now just a constant. Good? So if you recall in your, well, so this is your Hamiltonian. Is everybody with me? Yeah.
Like, only situation which you would be able to do is see your magnetic field.
Yeah. Because you're absolutely right. Like whatever direction magnetic field is pointing, I'm just going to rotate my basis and write it as if we define everything called z, right? But if it's changing, if the background magnetic field, it could be time dependent. If the background magnetic field is time dependent, which case am I in? I'm in case 2 because the Hamiltonian at different times commute, right? Just a coefficient that's time dependent. That's the coupling. All right, good. Are we good? Good. All right. So what are the energy eigenvalues for this Hamiltonian? Well, the only quantum observable is Sz. What are the eigenvalues of Sz? Plus minus h power over 2. So just plug in plus minus h power over 2. Here are your energies that I'm going to call E plus and E minus. There was a comment earlier that there's no ground state. There's no state with energy 0 here. Sure. So it's conventional to define a frequency, which is everything that's multiplying the Sz operator. Sc is now the sigma z, Pauli z observables, right? H bar over 2 Sc operator, sorry, H bar over 2 H bar times Pauli operator, Pauli z operator. Good? And this is a frequency. What's my evolution operator? Time evolution operator. Because it's time independent, Hamiltonian is time independent, it's just the exponential e to minus I omega over h bar Sc times t, where Sc is of course an observable, an operator. Good? Everybody's with me so far? Take an arbitrary ket as your initial state. What's an arbitrary ket? For example, C++ plus C minus minus. If you recall, in our notation, plus is Sz plus, right? These are the eigenkets of Sz with plus h bar over 2 and minus h bar over 2. It evolves as a function of time this way. The plus will be multiplied by e to minus I omega t over 2. Where did the h bar go? So I had e to the power of I Hamiltonian t over h bar. right? My Hamiltonian had SZ in it. The SZ had H bar as an eigenvalue, so the H bars canceled. Good. All right. So, for example, take S plus and S minus to be 1 over square root 2, and let's calculate what is the probability of observing, if you measure S of X at some time T, what are the probabilities that you might find that to be in Sx plus or Sx minus? That's a one-liner from what I've written down with these choices that you find in Sx plus with cosine squared of omega t over 2, and in Sx minus with sine squared of omega t over 2. If you using this, you can calculate the expectation value of S of X, right? You just add these two terms and you get H bar over 2 cosine of omega t. If you calculate the same thing for S of Y, you get H bar over 2 sine of omega t. You calculate that for S of Z, it's 0. So these are some quantum calculations. What does this describe? Can you describe the physics of this that we're seeing? We took a spin one particle, spin half particle, put it in a magnetic field that was in the Z direction. What do we observe? We observe that the expectation value of Sx is H bar over 2 cosine omega t, Sy is H bar over 2 sine omega t, and Sc is 0. How do you interpret that? What are we seeing? We see that this, you take a spin degree of freedom, you put a magnetic field in the direction of Z, you see that it starts rotating in the perpendicular plane, y-x plane, right? This is rotation. You see that in the perpendicular plane, it starts rotating. But it rotates with respect to observable, expectation value of observables. The kets are more complicated. So this reproduces your expectation from standard ordinary physics, right? If you have a magnetic vector with it, if you have a magnetic moment within some magnetic field with in the Z direction, it starts spinning in the perpendicular direction. Any questions? Yeah. Exactly. This is exactly the Schrodinger setup. At the time, within, yeah, actually, very good question. Very, very good question. So, when I was drawing these pictures, right? What do you learn? What was I doing? Here, I was turning on. Here, the magnetic field was 0. I don't want anything to evolve. Here, I turn on a magnetic field in the Z direction. Magnetic field is 0. Magnetic field in the X direction. Right? You don't want them to evolve in between. Otherwise, your calculation gets complicated. It was an idealization. All right. Any other questions? Not. Thank you so much, guys. Next time I'll go over, I'll try to include another example that the book has it, neutrino oscillation. Do you want me to go over it or not? It's a beautiful physics example. No, you don't want it. Okay. All right. Okay. Homework 3 is posted. Policy set 3 is posted. I'll post on my website. I'll post on Brightspace as well.